Hello, everybody. I'm going to be talking about Module 5. We'll probably break this into 3 lectures as well, because some of the problems towards the end of this module are a little bit of the more difficult variety, so I want to make sure that we're all on the same page. So let's get started with moles and why moles are so critical to chemistry. Let's start sharing. Okay, so we're going to look at the mole concept in chemistry. As a chemist, we often need to know the number of atoms in a sample of a given mass. And why would this be? Because anytime we have a chemical reaction or a chemical process, these things are happening between particles. So I have to make sure that I have enough of the reactants in my chemical reaction, or that I can predict the amount of product that I might be getting. So we're going to need to count atoms and molecules and ions and any other type of particle. And we're going to need to count them by using something that we can see. So we're going to use mass in order to count molecules and atoms. Remember, if we want to know the number of atoms in anything of ordinary size, we're going to need to weigh them. We can't see atoms. The only time we can see atoms is when there's many, 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 many of them together, and then that's going to be our liquid or our solid that we're going to be able to mass and measure using the materials and the methods that we're going to find out in lab. So the mole is really a chemist's dozen. We're used to describing larger numbers of objects with specific units. We know that 1 dozen objects is equal to 12 objects. When you go to the grocery store, you'll write on your list, get a dozen eggs. You don't write on your list, get 12 eggs, right? If you have a gross of something, that specifically refers to 144 objects. So if I have a gross of pencils, I would have 144 pencils. The same principle applies to chemistry, and the chemist's dozen is going to be the mole. This mole is abbreviated MOL, and the value of a mole is going to be this number, which is also called Avogadro's number. This has been measured experimentally, and it's been measured to a high degree of precision. So notice I have 1, 2, 3, 4, 5, 6 sig figs here. Typically, we are going to be able to use the first 4 sig figs. And that is what I'm going to hold you to when we do calculations and whatnot. This number is called Avogadro's number, and hopefully this will start to look like an equivalency statement, right? This is an equivalence. So from there, I can get conversion factors. So I know in 1 mole of anything, I'm going to have 6.022 times 10 to the 23rd of those particles. Now, like everything else, the mole actually has a standard, just like we talked about with different types of measuring devices or measuring units. So the mole is actually calculated by experimentally determining the number of atoms in exactly 12 grams of carbon-12, so the specific isotope, carbon-12. This gives us a unit for expressing macroscopic quantities, which are those composed of those microscopic or submicroscopic atoms and molecules, which are involved in chemical reactions. So as I mentioned, this is an equivalency statement, which gives me conversion factors. If I want to convert between the number of moles and the number of particles, which can be atoms or molecules or ions or formula units, right? Anything that pertains to chemistry is fair game in terms of what that particle is. I can use a similar method to convert between moles and number of particles. If I use the conversion factor, 1 dozen is equal to 12, right? For this conversion factor though, I use 1 mole is equal to 6.022 times 10 to the 23rd of those particles. So here are my 2 conversion factors. I have 1 mole of atoms or particles over 6.022 times 10 to the 23rd, or I have the inverse, depending on if I want to convert from moles to number of atoms or number of atoms to moles. So this is a guide. Here are my conversion factors from the equivalency statement. If I start with number of particles, I'm going to use this version of the conversion factor because I want number of particles to cancel out and I want to be left with moles. So this is going to be the moles in that particular example. If I want to convert from moles to number of particles, I'm going to use this version where my moles is going to cancel out and I'm left with number of particles in this particular conversion. Now, do you see why I want to use conversion factors? If I can use the conversion factors and use these decimal forms of those equivalency statements, I can follow the units to make sure that I'm doing it correctly. If I just memorize, oh, if I want to go to number of particles to moles, I divide by Avogadro's number. Or, oh, if I want to go from moles to number of particles, I multiply by Avogadro's number. You're going to get really confused really quickly. All you have to remember is that 1 mole is equal to 6.022 times 10 to the 23rd particles. You don't have to remember when you want to divide and when you want to multiply if you use the conversion factor method, because you're always going to put what you don't want on the bottom and put what you do want on the top. Then when I cancel units, I'm left with what I have. And if it's not the right factor, right? If it's not the right quantity, I did something wrong. So you can use this conversion factor method, this dimensional analysis, as a way to determine whether or not your problem is set up correctly. Here's an example. A pure silver ring contains 2.80 times 10 to the 22nd silver atoms. I'm looking for moles of silver atoms. So the number of atoms, which are silver, is equal to 2.80 times 10 to the 22nd atoms. I know that for every 1 mole of silver atoms, I have 6.022 times 10 to the 23rd silver atoms. Those are the relationships that I have. This is what I am given. I want moles. So I start with what I'm given, 2.80 times 10 to the 22nd atoms. I could actually start getting used to putting exactly what I have, which is silver atoms. I'm going to use Avogadro's number as a conversion factor. I want silver atoms on the top or on the bottom so it'll cancel, and I want mole of silver on the top because that's what I want to convert. I need to figure out the moles in this number of atoms. So my numbers are 1 mole is equal to 6.022 times 10 to the 23rd on the bottom. Notice this means my silver atoms are going to cancel and I'm going to get moles. So in my calculator, what I'm going to plug in is 2.80 exponent EE 22nd divided by 6.022 EE 23, and I'm going to get 0.04694961807. That's the answer on my calculator. Now I want to do an analysis of my sig figs. So to do that, I'm going to say, well, this value has 3 sig figs, and this value has 4 sig figs, because this is the definition and this is the measured. So I'm going to report to 3 sig figs. Now these are not significant because they're leading zeros. So I have this, I want to report to this value. So that is 0.04649. Because this is a 9, I'm going to report 0.0465 moles of silver. And this is going to be the answer to that question. I guess it's going to start raining or something. All right. Now, if I want to bring in mass or weight, right? I'm not going to be able to weigh out, you know, I'm not going to be able to count 1 by 1, 6.022 times 10 to the 23rd atoms. I have to be able to factor the mole quantity into a way that I can use this chemical in the lab by using the measuring devices that are available in a lab. So I need to be able to mass the mole, a quantity of a mole of atoms. So I'm going to use something called the molar mass. This is the mass of 1 mole of atoms of a particular element. This is really important here. We already know that on the periodic table, those weights that are listed, the average weighted atomic masses, are numbers on the periodic table, and typically for 1 atom, that would be atomic mass unit. That would be the unit for the mass of 1 atom, right? Molar mass is going to be in grams per mole. So grams per mole. That's going to be numerically equivalent to the element's atomic mass. So if I have 1 sodium atom, if I look on the periodic table, 1 sodium atom is going to be 22.99 AMU. 1 mole of sodium is going to have a mass of 22.99 grams. So the molar mass of sodium is going to be 22.99 grams per mole. And that's an important distinction to make between AMU and grams per mole. So we're going to go over it a couple more times. So molar mass is the mass in grams that is equal to the mass of an individual atom or molecule in atomic mass unit. The mass in grams of 1 mole of that substance is going to be obtained off the periodic table or calculated using the formula for the molecule or the formula for the formula unit. So for example, 1 atom of helium has a mass of 4.003 atomic mass units. 1 mole of helium contains this many atoms, and it has a mass of 4.033 grams. So the molar mass, which is this sort of capitalized, italicized big M, is going to have units of grams per mole. Now, this is an equivalency statement. For carbon, off the periodic table, I can write this equivalency. 1 mole of carbon atoms has a mass of 12.01 grams grams of carbon, or the molar mass of carbon is 12.01 grams per mole. Well, this is an equivalence, so I can get these 2 conversion factors. I can now have a method that will convert grams to moles or moles to grams using the mass on the periodic table. So here's some examples. On the periodic table, I know that 1 mole of aluminum has a mass of 26.98 grams. I also know from Avogadro's number that 1 mole of aluminum has 6.022 times 10 to the 23rd aluminum atoms. Everything goes through the mole. So I can convert from mass to moles, and then from moles to number of particles using 2 different conversion factors. Or I can convert from numbers of particles to moles, and then from moles to mass using 2 different conversion factors. What I cannot do is go to grams to number of atoms directly. I must go through the mole. Again, these are all values that are taken off the periodic table for those particular elements. This is the definition of 1 mole, which is Avogadro's number. Okay, so let's practice. How many moles of carbon are contained in 0.0265 grams of carbon? So I'm given 0.0265 grams of carbon, and I want to go to moles. Well, I know that 1 mole of carbon is equal to 12.011 grams of carbon. And this is going to be the molar mass, and I'm going to find this on the periodic table. So now I can set up my conversion factor. If I have this many grams of carbon, I want to go from grams to moles. So my gram is going to go on the bottom and my mole is going to be on the top. So 1 mole of carbon has a mass of 12.011 grams. So in my calculator, I'm going to go 0.0265 divided by 12.011, and I'm going to get 0.0022063109. How many sig figs do I have? I have 3 sig figs. Remember, these are leading zeros. So 3 sig figs. And I have 5 sig figs. So I'm going to report to 3 sig figs. So that means I'm going to report to there, because again, these are leading zeros and they're not significant. So I'm going to look at this 6. I'm going to get 0.00221 mole of carbon. Once I start getting this 2, 3 leading zeros, I might want to convert this into 2.21 times 10 to the minus 3rd mole of carbon. When my numbers get really, really large or really, really small, I start to think about the idea of maybe using scientific notation as a better way to convey that number. Here's another question. How many carbon atoms are there in a 1.3 carat diamond? Diamonds are a pure form of carbon, and 1 carat is equal to 0.20 grams. So here's another equivalence, which can give me a conversion factor. So let's look at what I'm given. I'm given a 1.3 carat diamond, which is actually carbon, because it says this is carbon. In addition to this equivalence factor, I also know that 1 mole of carbon is equal to 12.011 grams of carbon, and that 1 mole of carbon is equal to 6.022 times 10 to 23rd atoms of carbon. Notice how many carbon atoms. So this gives me a clue that I'm going to need to use Avogadro's number. All right, so this is what I'm given. I want to convert from carats to grams of carbon. So for every 1 carat, I have 0.20 grams of carbon. Well, I can't go from grams to number of atoms directly. I have to go through the mole. So I'm going to convert from grams of carbon to moles of carbon next. So 12.0, oops, get it wrong. 1 mole of carbon is 12.011 grams of carbon. So let's look at our canceling. Carats cancel, grams cancel. If I stopped here, I would be calculating the number of moles of carbon. But that's not what the question asked. The question is asking how many carbon atoms are there. So I need this 3rd conversion factor, where for every 1 mole of carbon, I have 6.022 times 10 to the 23rd carbon atoms. So my moles are going to cancel, and the answer to this question is going to be the number of carbon atoms in this diamond. So in my calculator, what I'm going to do is 1.3 times 0.2 times 6.022 second EE 23. I'm going to enter, and then I'm going to divide by 12.011. This is going to give me a very large number, and I can tell it's large because it's got a very large positive exponent. I want to convert to 2 sig figs. So I'm going to do 1.3 times 10 to the 22nd carbon atoms. That's because if I look at this, this has got 2 sig fig, this has got 2 sig fig, this has got 5 sig figs, this has got 4 sig figs. So 2 is the lowest number. My answer is 1.30357 blah 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 times 10 to the 22nd. So I'm going to round that to 2 sig figs. So this is going to be my answer to that question, to the right number of sig figs. This is how I want you to do this. I want to see a string of conversion factors on your paper. You could also write down the equivalencies if you want to. This is what I mean by showing your work. This is a perfect example of a show your work kind of question. And I want to be able to follow you and how your logic flows as you solve this problem. Now you can do it in stepwise, right? You can do the first step, and then you can do the second step, and then you can do the third step if you have to. At some point, I really want you trying to get this all to flow together and actually doing all the conversion factors in one string across the paper. Now that might not be where you are at now, and that's fine. You can always do something stepwise, but you want to be able to show me in detail using units and identity like carbon atoms, right? I can't just put atoms here. These are carbon atoms in order to show me that you totally understand what the problem is asking. Here's another a little bit harder problem. So let's go over this guy. I have a titanium cube, and this is the number of atoms. So this is the number of titanium atoms. I want to know the edge length of the cube. What I'm given is that the density of titanium is 4.50 grams per centimeter cube. This is a much harder problem. I have a couple of concepts coming in. I've got density. Remember, this is relating mass and volume together, right? That's what density is doing. I know my element is titanium, and I want to know what the edge length of the cube is. Well, if we draw out a cube, remember the volume of a cube is equal to length times length times length, or length cubed. That's my volume of the cube, right? So this is the formula that's going to give me my L, because my L is equal to the edge length of the cube. So that's what I ultimately want to figure out. So basically, in order to figure out the L, I need to calculate the volume. Well, the volume can be gotten using the density if I have the mass of the titanium. So what I need is to convert the number of atoms to moles to the grams of titanium and then get the volume of titanium. So I can solve it or stick it into this equation. So what equation or what conversion factors do we have? I know 1 mole of titanium is equal to 6.022 times 10 to the 23rd atoms of titanium. I know that 1 mole of titanium is equal to 47.87 grams of titanium, and that's off the periodic table. And I know from the density that for every 1 centimeter cubed, I have 4.50 grams of titanium. So this is going to be my density used as a conversion factor. So let's do this. I have 2.68 times 10 to the 23rd titanium atoms. I'm going to convert that to moles. For every 1 mole of titanium, I have 2.68 times 10 to the 23rd titanium atoms. Then I'm going to convert that to grams. For every 1 mole of titanium, I have 47.87 grams of titanium. And then I'm going to convert that to volume because I know from the density I have 4.50 grams of titanium for every 1 centimeter cubed. Let's look at our conversions to see if everything cancels in order to make sure that I set the problem up. Titanium atoms cancels with titanium atoms. Moles titanium cancels with moles. Grams titanium cancels with grams. I'm left with centimeter cubed, which is a unit for volume. So I am good to go. So what I'm going to do is I am going to put this in my calculator. 2.68 EE 23rd. I'm going to go across the top times 47.87, enter. Then I'm going to do divided by 2.68 second EE 23, and I'm going to hit enter. And then I'm going to hit, oops, I just did something really stupid. This is not that. This is my mole. 6.022 times 10 to the 23rd titanium atoms. All right. And why did I notice that? Because I got the molar mass. So I know I was actually doing something wrong. So let's do this again. My sincere apologies. But sometimes I like to leave these mistakes in because if I make a mistake, maybe you do. And when I go through the process of correcting the mistake, sometimes that helps you guys when you do this. I'd love to say this is all intentional. I intentionally make the mistake, but I'm a human. I make mistakes as well. So let's do this again. I'm going to go 2.68 second EE 23 times 47.87, enter. Divided by Avogadro's number, which is 6.022 second EE 23, enter. That gives me 21.304. Now, I have to go divided by 4.50 to get the right answer. So what I have here is this answer is the volume of the cube, which is equal to 4.734 centimeters cubed. Make sure you do the orders of operation correctly. If you're doing this in a string, if you divide by Avogadro's number, and then you're going to press enter, you need to divide again by 4.50. You could also do the top and then divide by and put this denominator in a parentheses. You'll get the same answer, the correct answer that way. What you won't get correctly is if you do the top and then you get an answer and then you divide by Avogadro's number and then multiply by 4.50. That will not give us the right answer. I'd have to divide by the product of 6.022 times 10 to the 23rd times 4.50. So I have to make sure I'm entering the order of operations correctly in my calculator. So pay attention to that if you're not getting the correct answer. Now, what is L? Well, I have 4.734 centimeters cubed is equal to L cubed. So what I'm going to do is take the cube root of that. So on my calculator, I go on and I press the math, and I go down to number 4, which is the cube root function. So then I'm going to put in that number I just got in my cube root, and I am going to get L is equal to 1.68 centimeters, because I'm taking the cube root of centimeters cubed. So that is going to be centimeters. So this is the correct answer to the problem. But you can tell it's a little bit more complicated because I had to correlate multiple concepts. I had to bring in density. I had to know the volume of the cube. I had to do a little bit more sophisticated calculations. So be on the lookout for that. This is a harder problem, but this is the type of problem that I will expect you to be able to master. Now let's look at formula mass. This is going to be the mass of an individual molecule or a formula unit. This can also be characterized as molecular mass or molecular weight. There are very subtle differences to the term molecular mass versus the term molecular weight versus the term formula mass. But basically, I get to these different terms differently, and they basically mean the same thing. I take the sum of the masses of the atoms in a single molecule or formula unit based on the chemical formula. Okay, so let's give you an example. I take, if I'm looking at H2O, I have, and I want to calculate the formula mass. If I only look at one molecule, recognize this unit is going to be atomic mass unit. So from the formula, I have 2 hydrogen atoms and I have 1 oxygen atom. So I have 2 atoms times the mass per hydrogen atom, plus I have 1 atom of oxygen times the mass of 1 atom of oxygen. You can do this as this conversion, but basically you don't have to put in this conversion at the bottom. You can just do 2 times 1.01 AMU plus 1 times 16.00 AMU. And when you get that answer, it's going to be 18.02 AMU. This is the formula mass. This is the mass of 1 unit. This could also be the molecular weight or the molecular mass, because water is in fact a molecule. So let's look at these little subtle differences. If I have a molecular compound, the mass of one molecule is going to be called the molecular mass or the molecular weight. I know weight is different from mass also because weight has to do with the force of gravity, but these are really used as synonyms. So if I want to figure out the molecular mass of carbon dioxide, I have one carbon atom and two oxygen atoms. I sum the atomic mass of the carbon 2 times the atomic mass of oxygen, and this is going to be the molecular mass or the molecular weight of carbon dioxide. My formula unit or my formula mass actually pertains more specifically to one formula unit of ionic compound. Remember, there's a difference between molecular compounds, which have that single most base unit as the molecule, and then ionic compounds, which form that lattice. So I really don't have one formula unit acting as a single discrete unit. I have, remember, this formula unit is the lowest whole number ratio of the ions that give me a net zero charge. So for sodium chloride, I'm going to add sodium, which is going to be 23 or 22.99 AMU because I have one sodium, and I have one chlorine, which is 35.45 AMU. I sum that together, and what I'm going to get is 58.43 AMUs. Now, just like before, I can look at the molar mass of a compound, right? The molar mass, and now it's a compound. It's either going to be a formula unit or a molecule. And this is going to be numerically equivalent to the molecular mass or the formula units or mass. And these are my units again, just like I did with the elements, the individual elements. The molar mass of a compound, which has that fixed ratio of elements that defines the identity of that compound. And that unit is going to be grams per mole. So the relative masses of molecules can be calculated from atomic masses. The formula mass is one molecule. That could also be the molecular mass or the molecular weight. So I have 2 times 1.01 plus 16. This is the formula mass. Note my units are in atomic mass units because that's just one molecule, the mass of the atoms that comprise that molecule in the unit AMU. If I have 1 mole of water molecules, this formula gives me another set of conversion factors. For every 1 mole of H2O molecules, I have 2 moles of hydrogen, and I have 1 mole of oxygen. So the molar mass for the entire thing is the sum of the constituents. 2 times 1.01 plus 1 times 16, that gives me 18.02 grams per mole, and that is going to be the molar mass. Again, that gives me a conversion factor because for every 1 mole of H2O, I have 18.02 grams of water. So I can use this as a conversion factor to convert between moles and mass of a particular substance. This is just going to be the molar mass in grams per mole, which will give me that conversion between grams and moles. I have to still go through the mole if I want to convert to number of formula units or number of molecules. So don't forget, I always go through the mole even when I do this type of a calculation. So if I want to go from mass to moles or mass to particles, I'm going to go from grams to moles to particles. I'm going to use the molar mass, and I'm going to use Avogadro's number. And if I want to go from number of particles to the mass, I'm going to go from grams to moles, from grams to moles to particles. Everything goes through the moles. I cannot go from grams to number of particles directly. I'm going to use the molar mass as a conversion factor, and I'm going to use Avogadro's number as a conversion factor as well. So let's look at these two examples. How many moles of calcium atoms are present in 20.0 grams of calcium? So I have a mass and I want to go to the mole. So right now I'm in this part. I'm going from grams to moles. I know 1 mole of calcium is equal to 40.08 grams. That's going to be that mass off the periodic table. So if I have 20.0 grams of calcium, for every 1 mole of calcium, I have 40.08 grams of calcium. That is going to be 20 divided by 40.08 to 3 sig figs. Because of this guy, I have 0.499 moles of calcium. Okay, now that's when I'm looking at my single element, right? Just my calcium. What if I want to look at a compound? This is an ionic compound because it's between a metal and a polyatomic. And I'm looking for number of formula units. And I have a mole. So I'm looking at this part of the conversion factor there. So if I have 5.32 moles of CaCO3, if I want to know how many formula units, I'm going to use 1 mole of CaCO3 is equal to 6.022 times 10 to the 23rd formula units of CaCO3 as my conversion factor. So here, for every 1 mole of CaCO3, I have 6.022 times 10 to the 23rd formula units. And that gives me 5.32 times 6.022 second EE 23, and I get to 3 sig figs, 3.20 times 10 to the 24th formula units of CaCO3. Now, I can also use grams. If I just have, this is a polyatomic or a diatomic molecular element. So the molar mass for N2 is going to be 2 times 14 because I have 2 nitrogen atoms. So the molar mass is going to be 28.0 grams per mole. Because this is the formula. This is actually a molecule. It's even though it's nitrogen, The formula for nitrogen present in nature is N2. So if I want to do 3.40 moles of N2 and I want to convert to grams, here, I'm going to take for every 1 mole of N2, I have 28.0 grams of N2. That's the molar mass used as a conversion factor. Moles of nitrogen cancel. I have 3.40 times 28. And what I get is 95.2 grams of N2. So remember, if I have a diatomic molecular element, your formula or your molar mass is going to be the formula of the molecule, which has 2 nitrogen atoms, N2. Now, what if I have a mass of chalk? Well, I need to figure out what the formula mass of that is. So 1 calcium is going to be equal to 40.08. I have 1 carbon, which is equal to 12.011. And I have 3 oxygens, so I have 3 times 16.00. I'm going to add that all up to get the formula mass, or the molar mass of CaCO2. So the molar mass of CaCO2, 3, is going to be equal to 40.08 plus 12.011 plus parenthesis 3 times 16 close parenthesis, and what I get is 100.091 grams per mole. So if I have 58.4 grams of CaCO3 and I want to convert to moles, I know for every 1 mole of CaCO3, I have 100.091 grams of CaCO3. The grams cancels. I'm left with moles. I want to go to 3 sig figs. So I do 58.4 divided by 100.091. And that's going to give me 0.583 moles of calcium carbonate as my final answer. So the next thing we're going to talk about is composition of compounds. That'll be divided into 2 lectures. So we're going to stop right here for the moment. Okay, you are ready to hit the ground running, calculating grams and moles and all that kind of stuff. So good luck. I'll see you soon.